Welcome to day 4 of our 12 days of Ec 10. Today's topic is general equilibrium, often shortened to GE. This is the last topic that was covered in the course. It's not in the textbook, so I advise that you watch this video in full carefully and review the lecture slides from Professor Mancu's last lecture, because you know this material is going to be on the test. It hasn't been on any other test so far, because it's so recent. So our starting point for general equilibrium is that we want to study, basically integrate our consumer choice model for one consumer, where we'd have a diagram, say, for Anne, that I labeled A here, and she chooses between X and Y, with Bob's choices. So we could make another diagram that looks just like this for Bob, but we want to put them together and kind of represent them all at once. So what we've done is we've rotated things 180 degrees, so that we take X and pull it up here, Y, rotate it down here, and we end up with Bob's preferences that look like this. You just read everything now from this point as the origin, and then as you move in this general direction, you get more of both X and Y. So when we put the two together, we get the Edgeworth box here, where we have Anne's starting point, Bob's starting point, and then we can look at any point within the Edgeworth box, say at this point here, and it would tell us how much Anne has for good X, that would be this distance, how much Anne has for good Y, that would be this distance, and then similarly for Bob, he has a lot of good Y because he gets this whole distance, but just a little bit of X, this short distance. And then now that we understand the Edgeworth box, we can discuss two important concepts. The first is Pareto improvement. So verbally, a Pareto improvement is an allocation that's better for one person and at least as good for everyone else. So in principle, you could have many, many consumers, like not just Anne and Bob, but also Charlie, Dick, Eric, and so on. And a Pareto improvement over any current position in the Edgeworth box would need to be better for one of them and at least as good for others. There's a geometric interpretation of this, which is probably more important for you to understand. And it's that suppose we start at point E here, so I've labeled E here, and we can draw an indifference curve through there. So we have one indifference curve for Bob that I'm highlighting in black, and we have an indifference curve for Anne that I'm highlighting in black too. And then any point on the indifference curve here for Anne are just as good. So point E, and then what I've labeled E1 up here where these two intersect again, is just as good for Anne, and then likewise point E and E1 are just as good for Bob. But if you pick any point highlighted in yellow, like all of this stuff here, you can see it's further out for Anne, so it's better for the same reasons that it's always better, more of both goods. And then from Bob's perspective, if you sort of turn your head, you can see that any point in the yellow area is also better for Bob because he gets more of both. And also the points on the edges of this area, so a point like right here, that would also be better for Anne and still just as good for Bob, so that would be a Pareto improvement. So essentially Pareto improvement geometrically is this almond-shaped area, everything in that almond, including the borders, with the exception of the endpoints. You know, E is an endpoint, and it can't be better than itself, so it's not going to be an improvement on itself. Our second definition that requires you to first understand improvement is Pareto efficient. A point's Pareto efficient, or the verbal definition, if there is no improvement possible. So if there's no way to make things better for at least one person without hurting anyone else, then you're Pareto efficient. You've kind of exhausted all the gains from trade. The mathematical version of this, if you've exhausted all the gains from trade, then you can't have people with different MRSs. You saw in problem set 7 with Roberta and Robinson that when people have a different marginal rate of substitution, you can find ways for them to trade. The person with the lower, who's willing to give up more of good X, is going to trade that away, and the person who's willing to give up more of good Y in exchange for little X is going to give up good Y, and they can make an exchange. But if they both have the same rate of substitution, they both are willing to make the same trades, then there's no way for them to trade and make each other both better off. And then geometrically, we know that if we have a point like, I'll call this F, so this point right here is F. At point F, we see there's an almond area, right? It's like the yellow area of Pareto improvement. So F is not Pareto efficient. There's a set of improvements that we can highlight. So if we're going to have a point that's Pareto efficient, there's going to have to be no almond shape. And the only way to get that is we can't have the two indifference curve intersect at 2 points and create that almond. They're going to have to intersect at one point, be tangent to each other, hence the MRS A equals MRS B condition. So our graph will look kind of like it does here at point E, where they're back to each other, only cross at one point, there's no almond to see. So there's no gains from trade to be had. So then we get a few more definitions. If you understand improvement and efficient, that's pretty much most of what we want you to understand. If you can draw an Edgeworth box, look at a point, compare it to some other points, and say, hey, look, this point has improvements. A, B, and C are improvements on D. If you can say D is efficient, A, B, C, and all the other points are not improvements on it, there are no improvements on it, then that's pretty much you got everything that you need to get out of the lecture. But there's a few more definitions that it's nice to know. One is the contract curve. Contract curve is the set of all efficient points. So Pareto efficient, of course. So the contract curve will be a whole bunch of points that look like E. So if we had point E here, and we know it was efficient because it was two indifference curves tangent, we know there's a whole bunch of other points like that. I could call this E2. and say that we have two different respect to it. And there will be a whole bunch of points like this. We'll have a contract curve that looks like this. Usually they're points towards the middle, right? Because if we had a point out here, probably people are not totally happy with having, Ann having a ton of good Y and hardly any of good X, and Bob having a ton of good X and hardly any Y. They're probably going to want to trade, so that's not efficient. The points where people don't want to trade anymore are usually in the center, hence the contract curve's in the center. And then let's consider a point like, we'll call this E3. And E3 is not efficient, so it's not on the contract curve. So it has a set of improvements over it, has that almond-shaped area. The core is a set of efficient improvements. So they're points that are on the contract curve and are Pareto improvements on the point. So the core has to be defined with reference to some like starting point like E3. So if we started at E3, we can see there are sets of improvements, it's all this space, but the core is only the ones that are Pareto efficient, so they'll just be the ones that I'll highlight in red here. Just these points. Whereas all of these highlighted points that I'll go over, that we're running over here, these are all on the contract curve, but only the red ones here are part of the core. So contract curve, efficient in general, any efficient point, core, efficient, and an improvement on the initial point. So this is a market, right? So one thing that probably stands out that really is kind of wacky in a way is that we haven't talked about prices at all. We've talked about efficiency, Pareto improvements, the core, contracts, but we haven't talked about prices. There is a way to introduce prices in this model. We can just like give some random prices, PX and PY for the goods, and then that would induce a budget constraint because the people only have so much money, so they can only buy so much. But there's no guarantee those prices are the right prices. They're not necessarily the equilibrium prices. So we went on to talk about how you could find. So like the open question is, how can we find P star, the equilibrium price vector, and we went on to talk about this kind of idea of a Walrasian auctioneer. And the way he does things is that you start out with some, random price. So like random price. And then you look at what people choose to buy. So we start at a point E here. These are what people are endowed with. We pick some random prices for good X and good Y, and then that induces a budget constraint. Not really important that you're able to draw this budget constraint because it's actually pretty technical. But you can see how it induces, if I gave you some prices for X and Y, it would limit your choices, and then Bob would pick his optimal point. So Bob picks this green point here on his budget constraint, and Ann picks her optimal point on her budget constraint. They share the same budget constraint because we've drawn the graph so that they're like, Bob's is 180 degrees, like discussed earlier from Ann's. So now that we see Bob and Ann have made their choices, we see there's a problem with this P. Bob is choosing to consume this much, I'm highlighting in blue, of good Y, right? And Ann is choosing to consume also a lot of good Y. And when you put these two together, you can see if Ann is consuming all of this Y, and Bob is consuming all of this Y, there's excess demand. So the second is like, is there excess demand? And then here there is. So that tells us that we need to raise the price of good Y. Like everybody wants to buy Y. There's way too much. Like Ann and Bob can't both get more than the total quantity of Y. These two blue lines need to add up to the total width. So if there's excess demand, then you raise PY. So we'll have to raise the price of good Y. Then the budget constraint will change, and as we raise the price of good Y, as long as the goods are normal goods, we'll see demand go down. And eventually, if we raise the price enough, we'll get no more excess demand. If we raise it too much, now we have like a deficient amount of demand. We'd have excess supply. So we talked about in lecture how Bert and Ernie could have like excess demand for cookies, and then we need to raise the price for cookies. So eventually, through this kind of complicated mathematical process, you'd use a computer to actually solve this in practice. You can go through this auctioning process and find a PY and a PX that actually make the market clear. And then the last thing we talked about are the welfare theorems. So the first welfare theorem is that when you go through this whole process of the Walrasian auctioneer calling out prices and eventually setting on one to get rid of the excess demand, that point, that market, what the market produces, so the market equilibrium, we'll highlight. So this is what the market gives us, and this is what we define, and then that gives us a point that's efficient. So pretty much the same thing we said for our studies back in Chapter 7. What the market does for us is good in the sense of it creates lots of gains from trade and it exhausts all those possibilities. You can't really do better than the market, in a sense. And at least in that one sense of Pareto efficiency. The second theorem is that you might not like what the market produces. The market might produce an efficient point where Ann gets almost everything and Bob gets, crumbs off the table. So Ann gets 9 cookies and 9 cups of milk, and Bob gets like 1 cup of milk and 1 cookie. So that might be really inequitable. If you don't like that, you can get a different point just by changing the starting point. So you can just like take a lot away from Ann before the trading takes place. Just take away a whole bunch of her milk or take away a whole bunch of her cookies, give them to Bob, and then he can either eat them or he can trade them. the market will get us back to an efficient point. So you don't have to worry about it ruining efficiency by taking away from Ann. You just worry about making sure that Bob gets his whatever he thinks is his fair share. These welfare theorems are pretty generally applicable in theory, but they don't apply when there's externalities. So let me say not. They don't apply if there's externalities, if people are dumb. So that's what we call, behavioral economics, the stuff David Laibson talks about in lecture. If people make dumb choices, then their choices aren't going to make them happy, so they're not going to get a lot of welfare from the market. If you go to the gym and you buy a gym membership and then you never use it, then it's hard to say that that was really good for you, that you benefited from it, that the market did something good for you. And then not if there's asymmetric information. So not if, like, the buyer or the seller knows more about the goods. So if you feel like when you go to Walmart or if you go to a mattress store that the guy who's selling the mattress knows more about the mattresses than you, then this theorem that the market's going to give you good outcomes doesn't apply. Greg talked about in his second to last lecture how liberals and conservatives disagree on how common they think market failures are. So how common are externalities? How dumb are people on average? How often are there information problems in the market? I think the general consensus is that these are pervasive. So these welfare theorems have essentially no applicability whatsoever to any real life scenario. The real question is how close, like how good of an approximation are there? It's never going to be perfect. These theorems will never actually apply, but they might be a pretty good approximation to the market. And conservatives will tell you they are a relatively good approximation. Liberals will tell you they're terrible. So in summary, most important things we learned far and away are definition of Pareto improvement. It's an improvement if one is better off. That looks terrible. And then everyone else just as good. And then geometrically, that's the almond-shaped area except for the ends. And then efficient if no improvement possible. You need to be able to recognize these geometrically and reason about them verbally. So if I told you that we've reached a point where we can't find any gains from trade, there's no way to do a Pareto improvement, then you should recognize that as efficient, even if you don't see a diagram. And then last, we really talked about pricing pressure. Basically, the Walrasian Auction here is just a fancy way of talking about pricing pressure from our very first unit or second unit on supply and demand. If there's excess demand because everybody wants to buy lots of cookies, and you add up those two heights and you see people buying too much, then you raise the price. If you see that nobody really wants to buy the Y good, then you lower the price, and you get if you have excess demand, you raise the price. If you have excess supply, you lower the price. It's exactly the same as in Unit 2. So that pretty much sums up everything you need to know about general equilibrium. You will see this material in the test. It is difficult material. It's not in the book. It's an advanced topic that's usually not taught in a principles course. If you find it confusing, that's fair. Just try to understand these two main terms, Pareto improvement and Pareto efficient, and you'll do fine on the test. I wouldn't recommend spending more than an hour or two on this topic because there's so much more material in the 22 chapters we covered. This was just one lecture. Thanks for watching.